Okay, ladies and gentlemen, my name is Raymond Young. This morning I have great pleasure and honor to introduce Professor Andrew Yao as the first plenary speaker of ISIT 2006. Professor Yao was born in Shanghai, China. He received a Bachelor of Science in Physics from National Taiwan University, a PhD in Physics from Harvard University, a PhD in Computer Science from University of Illinois. His research interests include analysis of algorithms, computational communication complexity, cryptography, and quantum computing. From 1975 onward, Professor Yao served on the faculty at MIT, Stanford, UC Berkeley, and Princeton University. In 2004, he left Princeton to become a professor of computer science at Tsinghua University in Beijing. He's also a distinguished professor at large at the Chinese University of Hong Kong, where I first met him. Professor Yao was recipient of the prestigious A.M. Turing Award in year 2000 for his contribution to the theory of computation, including communication complexity and pseudo-random number generation. He has received numerous other awards and honors, including the George Polier Prize from Siam, the Donald E. Knuth Prize from ACM IEEE, and several honorary degrees. He is a member of the U.S. National Academy of Sciences, the American Academy of Arts and Sciences, and the Chinese Academy of Sciences. Professor Yao is going to talk about his perspective on computational and communication complexity. Without further ado, let me introduce to you Professor Andrew Yao.
Good morning. It's a great pleasure for me to be here, and I'd like to thank Professor Raymond Young and the organizers for giving me this opportunity to meet with you. This symposium is about information theory, which deals with the question, how efficiently can you transmit information in a network situation? And it is one of the pillars of the scientific foundations of the information age. And the other pillar in the information age, scientifically, is theory of computation by Alan Turing and others. And my area is in computational complexity. And so today, I would like to tell you a little bit about my personal perspectives of computational complexity, its developments in the last 30 years or so since I entered this field. And on paper, computational complexity seems to be very different from communication theory, because in computational complexity, we deal with the question how hard it is to perform computations. And however, as you will see, that most of the developments in the last 30 years in computational complexity turns out to be driven by questions in communications. So today, I would like to share my thoughts on this subject with you. And so there are two things I would like to accomplish. Firstly, I'd like to give you some idea why these developments of computational complexity have something to do with communication problems. And secondly, I would like to show you some of the open problems in computational complexities that can be phrased as communication complexity. Let me start with a little history about computational complexity. It is really called theory of computation, and it started in the 1930s. And so the exciting things about theory of computation in those days was about the undecidability of questions. So it turned out that there are some natural questions in computation that turns out to have no good algorithm. Not only no good algorithms, but they couldn't have any algorithm at all. And so for the first 30 or 40 years, the main emphasis was in understanding what problems turned out to be undecidable. And this started to change in the 1960s when computers becomes as a real hardware available. And so people turn their attention to questions not about whether something can be done, but whether computations can be done in a practical and efficient manner. And one breakthrough that happened was the consideration of polynomial time as the criterion for whether some algorithms can be done at a practical level. And I think that that turns out to be an important thing. It's a very simple idea to define what one means by efficient computation. However, it works like a platform. Since that time, since the 1960s, computer scientists had a common language to scientifically discuss the question of complexity. And in 1970, Cook, Karp, and Levin, they started the notion as non-deterministic polynomial time. And the problem of NP and the discovery of NP-complete problems turns out to be a watershed in the theory of computation. And my own career started in the early 1970s when I entered the field and when everybody was excited about the question of NP and NP-complete problems. And that excitement turned out to be very well-grounded because for the last 35 years, almost everything in computational complexity was driven by that central notion. And so what I would like to do is to tell you something about what happened in the last 35 years since the concept of NP-complete was raised. And of course, it's a very large field, and I will not really give you a complete survey of the area, but I will just give you my personal thought, give you a very biased view about what are the underlying themes of all these developments. And so the outline of the talk, first I'm going to discuss some recurrent themes underlying these developments. And then I'm going to give you my thoughts on the status of complexity theory, and then I will discuss some open problems. I'm going to discuss three recurrent themes in the developments, the power of reduction, and the power of communication, and the power of mathematics. And I'm going to put a lot of emphasis on the power of communication because it's relevant to this conference. If there's one major technique, if there's one native technique in theory of computation, it is the technique of reduction. And the basic idea is very simple. Suppose you have a certain problem that you know that it's difficult. And if you can show that this problem is reducible to another problem, in the sense that if you can solve problem B, then you can solve problem A using the algorithms for solving B as a subroutine, then you have shown that problem A that problem B is more difficult than problem A. And so the beauty of the NP-complete concept is that it shows that hundreds or even thousands of many of the questions people have been interested in operations research and optimization turn out to be all equivalent to each other. And people had been puzzled by the fact that somehow all these hundreds of problems turn out to be very resistant to attack, even though they look like reasonable problems. And the concept of NP-completeness showed that there's not a million mysteries why all these problems are difficult, but really there's only one single mystery, and because they are all reducible to each other. And so even within the first 10 years, the method of reduction, well, by the way, the method of reduction actually was inherited from the mathematical logic and theory of computation. And so even within the first 10 years, people have solved most of the mysteries that why certain problems were difficult. However, exceptions exist. And there are questions, especially optimization problems, for which that people have not been able to understand why these problems are difficult even in the approximate sense. Let me just give you a single example. That is the question of finding maximum cliques in a graph. So if I give you a graph and a subset of vertices are said to be a clique, if within this subset there are edges between every pair, there's an edge between every pair of vertices. And so I think that it is something that is familiar to information theorists. If you have an alphabet, and now if letters can interfere with each other, and if you put an edge between two letters, if they interfere with each other, then the finding of a good large clique is to find a subset of letters that you can transmit without any interference. And so now it's clear that finding maximum clique, there's a trivial algorithm, namely that I can just take one single vertex. And so that's a trivial algorithm which gives you a clique of size 1. Now, so the ratio of the maximum clique divided by what you have found by this method is at most n. And it turns out that you cannot do much better than this. So all the efficient algorithms that people had found, none of them has a performance much better than this. So in essence, nobody has found a good efficient algorithm that can find a maximum clique such that its ratio with the maximum, the optimal solution within n to the 1 minus epsilon. So that had been a mystery since the very early 1970s. And now, since 1980, the industry of finding reductions among problems turned to become very sophisticated. And the reason for this turn of event were two things. One is the idea of randomization. So the idea that it's possible to use Monte Carlo method for general computing purpose turned out to be a very powerful concept. And so people were able to find reductions not just among deterministic computations, but also for randomized algorithms as well. And now the second ingredient for this turn event is about cryptography. And in cryptography, you have a development of a situation where if you want to solve problems, you have to find reductions from protocols to problems instead of just between problems. And that involves very much more sophisticated reductions among the problems. And just to give you a feeling on how randomization and cryptography affected the level of sophistication in the reduction technique, let's consider one-way functions. One-way functions is a function such that it's easy to compute one way, but it's hard to invert. So if I give you an input x, it's in polynomial time, you can compute f of x. However, if I give you the value of y and would like you to find an input x such that fx equals y, then it turns out to be difficult. Now, so from the point of information, you might describe it as follows. If I know the value of y, then there is some information about x is not accessible. Well, we know that suppose this one-way function is 1-to-1, then in the strict Shannon sense, knowing y, then everything about x is known, because you can invert it. However, if you put the computation consideration into play, then the fact that you cannot always invert y intuitively means that there's some information about X, although it is available in the Shannon sense, but it's not available in the computational sense. And therefore, you can say that it's computationally inaccessible. So what it means is that there's some computational information in this transformation. And cryptography is an interesting subject in the sense that it is a true interdisciplinary field between information theory and computation theory in this sense, because in the Shannon sense, the security of information doesn't apply to the setting where you have public key systems. And so in order to discuss the questions scientifically and incorporate the computational complexity into consideration, you have to manipulate information using this concept of computationally accessible information. So for example, suppose I have k instances of yi equals f of xi. And let's suppose that the last bit of the x is a hard bit, in the sense that if I give you yi, not only you will not be able to invert it and find out the value of xi all the time, but actually just to estimate what's the last bit of the of x, it's somewhat hard. So there's some inaccessible information about the last bit of x. So in the practical sense, what it means is that if I give you yi, then the value of the last bit of xi, it's mildly unpredictable, in the sense that, well, you may be able to predict it with 95% of probability, but you'll be wrong 5% of the time. And now, if I have k instances of this, and I look at the parity of the last bit of all the xi's, then it turns out that the parity is strongly unpredictable. So this is not a very deep phenomena in the classical case. In the classical case, suppose you have a binary channel, 0 and 1, and there's a 5% probability that 0 will become a 1, and 1 will become a 0. And now, so if you look at the transmitted symbol, then the advantage that you have in predict what the original symbol is at most it's just 90%. It's 95% minus 5%. However, if I transmit this case symbols independently through the binary channel, and I ask you what's the parity of the original xi, how many, whether there's an even number of ones in all the xi's or there's an odd number of them, then it's very easy to see that this parity is very strongly unpredictable. Actually, it's, if the original advantage is epsilon, then it becomes only epsilon to the kth power. And it's a very simple calculation, and because you have an exact formula that you can do. Either you can write it down explicitly, or you can do it by induction. Now, however, this phenomena in the computational sense is very, so this sentence here, in the computational sense, is non-trivial, because what you need to do is to say that suppose in a single case, every algorithm try to make the prediction has to be wrong a certain percentage of the time. You'll have to show that the parity will become highly unpredictable as a consequence. So what you need to do in order to prove a statement of this kind is to show that suppose you have a polynomial time algorithm such that you can predict the parity with advantage epsilon to the kth. Then you have to demonstrate you can use this algorithm as a subroutine and come up with a polynomial time algorithm such that you can predict a single instance, the bit of xi, with advantage epsilon, with a much improved efficiency. So in principle, what you need to do is to use reduction in order to prove this statement here. And this is a special case of the XOR lemma. So this bit actually doesn't have to be the last bit of xi, but an arbitrary predicate of the problem would do. And results of the kind that I mentioned was needed in order to perform even more sophisticated reductions among cryptographic protocols. And it turns out that this kind of considerations not only is good for cryptographic purposes, but it actually sheds some light, actually sheds deep light into the theory of computation itself. And from very early on, one realizes that using such reductions, you can show non-obvious insights, non-obvious theorems about computational complexity. For example, from very early on, it's known that if you have something that can be done by Monte Carlo method, then it can be done in a deterministic way in a much more fast manner than the obvious method of enumeration. And now, from that time on, the idea of making use of these reductions to produce results about complexity time and time again comes up with stronger and stronger results. And let me just, I cannot list all of them, and let me just highlight it with the latest. This is a result in 2005 by Omar Rango. It shows that something called ST connectivity has a very non-trivial algorithm. So let me explain a little bit about this question. The ST connectivity is the following computational problem. You are given a graph G, an undirected graph on n vertices, and you are given two nodes, S and T. And you would like to decide whether there's a path that connects you in the graph from the node S to T. And now, this question is trivial to do if you don't care about how much space that you use. It's a very standard problem in algorithms. However, let's consider the following model, that the graph is given to you in a certain storage. And let's try to minimize the additional space that you need to use in order to do this problem. And so it becomes very non-obvious how to have an efficient algorithm to use a minimal amount of space. And from very early on, it's been known for 30 years that if you are willing to use log n square time, log n square space, then ST connectivity is in this complexity class. It can be done using log n square bits of additional memory. However, it has been an open problem whether you can do it in log n additional space. And through a progression of reductions, starting from this very early time, after 30 years, certainly last year, Rango came up with a proof that gave an algorithm that is deterministic and use only logarithmic n number of bits to solve the ST connected problem. And this certainly it's perhaps the most exciting result in the last 5 years in computational complexity. And so I think this is something that is really remarkable in the sense that we went through all this idea of reductions and random and cryptography, and eventually we have obtained a result which has nothing to do with randomness. And it's purely is a question that is concerned with the classical computational complexity, but you have to go through this detour in order to find it. And it's certainly, I think it's an example of how scientific results build upon each other. And you have to obtain the answer to questions by just some random walk. And now I want to come to the item of the power of communication, second recurrent theme in the development of recent computational complexity. And now, the technique of reduction were able to show its power in the last 30 years only because there's a stage on which to perform reductions. And so basically, most of the greatest stage actually is provided by communication. And this is not surprising considering the development of computation. In the last 20, 30 years, computation have come from a single machine computer to network computers. So computers have to collaborate with each other in order to perform many useful computations. So therefore, the theory of computation, the idea of computational complexity has to be developed for a multi-computer, namely a network environment that will take the communication into account. So let's just call it interactive computation. And the simplest case is just two computers, Alice and Bob, and each one of them has some input X and Y, and they like to communicate with each other in order to get some, perform some useful purpose. And now I will restrict myself to just three items. And I have talked about cryptography. So cryptography is a situation of this kind, except that the computation is not just for the purpose of obtaining some answers, but also the computation has to be done in order to satisfy some privacy, some fairness requirement. And the second item on the list is about communication complexity. And this addresses a different kind of criterion, namely that Alice and Bob would like to perform some computations and obtain answers for each one of them such that the amount of communication is minimized. So in some sense, this is a very pure consideration that extends the Shannon's information theory. In the Shannon case, you are mostly interested in the case when the information X, some information has to be transmitted to some other places. Now here, we have to consider the more general situations where you are interested in answers that involve as a computation. And the third is about some more complicated, but more innovative models of computation when you have many computers around. And now, communication complexity has been studied for since 1980, and one big surprise is that it turns out that the studying of communication complexity questions results in interesting results in classical computational complexity. And now, the communication complexity, as I have described it, have applications to VLSI design and Boolean circuit and so on. And now, depending on what kind of computational models you are using, the communication problems would look a little bit different. I mean, for example, in a very interesting model interesting variation of the communication complexity model. Koshmar and Wigderson showed that the Boolean circuit depth is exactly equivalent to some version of communication complexity for the function. And so the depth of the circuit for computing a function is equal to the amount of communication that is needed. And I'm going to return to tell you what this is all about toward the end of the talk. But the big picture is that the studying, so if you like to obtain results about the classical computational complexity, sometimes it's worthwhile to look at it in an alternative way and phrase it as a communication problem. And now, in some sense, this shouldn't be a surprise, because when you think about it, computation is very much related to communication. Every computation, every computer, or even network computers, they would always consist of elementary components that are communicating with each other in order to get the communication done. And now, so far we have talked about two things. One is that the cryptography provides the natural stage in order to test out the ideas of reduction and the techniques of computational complexity. And the communication complexity gives you some handle to look at computational problems as communication problems. And now finally, the interactive proof is addressing the question that in the network environment, how can you extend the ability of a single computer computations? With many more computers, what's the limit of knowledge a person can get through interactions? And it becomes much easier. And there have been a lot of, it turns out that suppose you have a computer that has a limited computation power, then of course the range of your knowledge, the amount of knowledge and the quality of knowledge you can find out is limited by your computational power. And now suppose in the network there are much more powerful computers. There are much more resources for computation. How can you take advantage of them in order to obtain those knowledge? And now here, of course, the question becomes non-trivial when you when you consider the situation where you don't want just to get the knowledge, but you actually would like to be able to certify that the knowledge that you are given is accurate and reliable. And when you consider this, then there are very interesting things that you can say. For example, let's just consider the question of finding a maximum clique. And in a maximum clique, if you have a all-knowing computer, say, let's consider a knowledgeable a professor who can tell you that this very large graph has a very large clique. And one way he can convince you, the student, is to write down a proof, namely that the professor, all he has to do is to show you the particular set of nodes that form a very large clique. And then the student can just go and check it. And in this way, the students get knowledge. So that's the classical concept of mathematical proof. Now, however, suppose you're considering the following situation. You have very lazy students, and the students doesn't want to read through n bits of information in order to check it's really a clique. And what the students want to do is he wants to put the burden on the professors. And he asks the professor to write the proof in such a way such that the students can just randomly turn a few pages and look at a particular line and just to check the local consistency. And it turns out that one of the big discovery is the probabilistic Chekhov proof, which says that this actually is indeed possible. So this really solves one of the at least conceptually, one of the problems that we all want to do actually as professors. Because when we give exam, when you try to design exam problems, you want to design hard problems, and you want the students to spend a lot of time working on it, but you want it, the proof is written in such a way that's very easy to grade, very easy to check. So if you adopt this system, you can ask the students write the proofs in a certain way so that when you grade the exam, all you need to do is just to turn some random page, look at some random line, and just the proof. Just check 3 or 4 places, and you can get the right answer. So now, that by itself is a very interesting theorem, but it actually, something more remarkable happens is that it turns out that this is related to solving the mystery that I've just mentioned, that this provides you a way to do the sophisticated reduction so that you can show why it is hard to find large cliques. And the third recurrent thing is the power of mathematics. And in the last 30 years, the reason that the field is very prosperous is because the mathematical techniques that have been developed for solving problems in this area becomes much more multifaceted. And when I entered the field, I think that the level of mathematics for solving problems was very low. However, the last 30 years, many great mathematicians from pure mathematics have entered into the field, and they have brought very interesting techniques to all these areas. So let me just show you an example of what I'm talking about. In information science, we all talk about decision trees. So one particular type of problem could be the following: if you have a subset of the Euclidean space, and you like to solve the membership problem. So if you are given a point in the Euclidean space, you like to decide whether this point belongs to the subset of S. And this is a very commonly used model when we are dealing with geometric problems in computations. And now, so the natural question is that suppose S is a algebraic set, something that is defined by polynomial equalities and inequalities. And the natural complexity model is that how many operations you need in order to solve this problem in the arithmetic sense and the branching sense. And so it turns out that one can relate the computational complexity in this model to some classical notions in topology, namely that it turns out the number of operations is bounded by the logarithm of the Betti numbers in the topological sense. And so that's what I mean, that the power of mathematics enables you to prove problems which it will be very hard to do if you started from scratch. And now, having all this reviewed the 3 recurrent themes and some of the achievements, where are we as a scientist in the computational complexity theory? And now, first, I think that we are very good at finding relations between problems, and we are also very good at exploring new horizons. We have a new computing environment, and we know how to phrase the questions, and we can find relations between problems, and we can manipulate information in the computational sense very well, and for example, in cryptography. And however, and also we have very good progress in proving lower bounds in some structured models. So if you don't consider the most general computational model, and if you consider programs which solve problems based on some logic, then we have very good success in showing what the optimal algorithm is. However, we have very little success in deriving lower bounds for general models. So in other words, we are very good at showing that something can be done, and through the various reductions. And we are very good in showing that some question is as hard as some other problem, but we are very bad at showing that some problem is just intrinsically very, very hard in the absolute sense. And so the greatest challenge that have been facing us in the last 20 years and also in the new century is to prove strong general lower bounds, because eventually, as a mathematician, we would like to be able to show that something is really hard. For example, we really want to show that factoring is intrinsically very hard in order to have a true good foundation for applications such as cryptography. Now, however, this central question is much beyond us. Now, I think that many computer scientists have given up, but I'm one of the optimists, and I think that there's still hope. And I think it's still. I think one thing that makes me optimistic is that I've seen all this great progress in solving great mathematical problems that have lasted for centuries. I mean, we have seen the Fermat theorem and the Poincare conjecture. So I just don't think that the questions such as P&P problem could be harder than the Poincare conjecture. Okay, so now here's some random thought that firstly, I think it's great to have unsolved problems, very hard problems for a field. And now, how do we go about solving them? And my thinking is that we really cannot hope to do it within a short time. We have to do it just like when people try to solve deep, pure mathematical problems, have to do a lot of foundational work. And now, how do you decide what to do? There's a very nice hint that has come up 10 years ago. It's called the natural proof concept. What these authors show is well, actually, what they said at first sight seemed to be really depressing, because they show that many of the techniques, actually most of the techniques that we have been using are intrinsically not possible to prove strong lower bounds. And essentially what they show that, at least for problems such as in circuit complexity, that if the proof method is constructive and large, and so large means that if the techniques would apply to random functions. So what they said is that if the techniques is applicable not only to a particular function, but actually would be to random functions, then such proofs are doomed to failure. Okay, and so this, I think, is a great progress in the positive sense, because it tells you where not to look. And so I think that the real answer is that we should look at deep analysis into specific functions, because we shouldn't be looking at techniques which would work for random functions. But I think that is consistent with what mathematicians have done, is that you can prove things about some very specific functions that have great structures. And I think that's where we should look at. And finally, let me just end the talk by showing you some open problems in this area. And I will give examples in this different aspect. Firstly, about Boolean computation. Well, of course, the P&P question is I think it's the holy grail. And however, we don't really know any non-trivial strong lower bound. So now here is a question that that's easier than a P&P question, but still it would be a tremendous landmark. If you can solve this problem, it will be the biggest progress in the last 30 years in computational complexity. And that can be phrased as a communication problem. So let me tell you what this is. This is taken from the Kosmer and Wigderson communication complexity model that I showed you before. And let's consider the following communication problem. Alice and Bob has inputs. These are graphs. So X is an n-vertex graph, and y is an vertex graph. And X is Hamiltonian. And Hamiltonian means that it's a graph that has a cycle that would visit every vertex exactly once. So one huge simple cycle. And Y is non-Hamiltonian. It doesn't have such a cycle. And of course, X and Y now has to be different because they have different properties. And therefore, there has to be at some place that they are different. So meaning that there is some pair of vertex such that there's an edge in one of the graph, but not in the other graph. And so the purpose of the communication is so that you will be able to locate one such edge. It doesn't matter which edge, but one such edge. So the conjecture is that there's no way there's no protocol, no communication protocol such that you can do it with logarithmic number of bits. So of course you can do it in n squared bits because Alice can just send the whole thing to Y. So the question is that is it possible to do it in much better than that? So can you do it within a logarithmic number of bits? And so this would be a wonderful breakthrough in computational complexity. And now that I suspect it's a very hard problem. So let me turn to something which might be a little bit simpler, but still you'll be a very big result in computational complexity. Let me just look at the following communication problem. Okay, so you have K+1 processors. So they are K+1 computers, and now P1 to PK, they have inputs and X1 to XK, and each one of them is a long binary string, n-bit long. And now PI knows all the inputs except Xi. So this is a kind of a different model from the natural model. Is that it's the classical model where a kid has a number on his own forehead. And so he can see all the numbers in other people's forehead except on his own. Okay. So the question is that if these kids, they would like to compute a certain function depending on the input, and so they all send a message to Q, and would like Q to be able to find out the answer to this function. What is the minimal amount of work that you have to do? And so it's clear that if K is very large, then the computation becomes easy. But the question is that for moderate large K, so for example, if K is a polylog in the N, and can you find a function f such that its complexity is bigger than polylog? And so we don't know any explicit function for which that one can, although you can show by probabilistic argument that almost all the function has property, but however, one doesn't know how to do it explicitly. And there are some functions that some candidate for doing this, and I can tell you offline. And in geometric questions, and the big question is how to show a non-information theoretical lower bound. The logarithm of Betti number is essentially an information theoretic lower bound. So the question is that, can you do it? Can you prove non-information theoretical lower bound? One candidate is the three-sum problem, and this problem is very easy to describe. You have n real numbers, and you'd like to know whether there are three of them that will sum up to 0. And let's consider the decision tree model in which that you can ask question a linear function of x to see, it tells you whether it's greater, equal, or less than 0. And finding out the result, you can choose the next function. So you can just imagine you have a bunch of hyperplane in the space. You'd like to know whether the input point is on this the union of this plane. And now the question you are allowed to ask is to pick a plane, and you get the answer whether the point is to the left or to the right, and then you pick the next plane. So the question is that how many times you have to do it, and it would be great if one can show. I think this is a big, very good candidate. And the third, let me just mention exciting developments in computational complexity is about algorithms in quantum computers. And we know that there's a very famous algorithm for factoring large integers. And the biggest problem is to find a polynomial time algorithm for a classically hard problem other than factoring and related number theoretical problems. And some people think that the graph isomorphism problem might be such a problem. And finally, let me just tell you there's a great communication complexity problem that is open. So the question is that if you are allowed to use quantum messages between computers, is it possible to get an exponential speed up over the classical one? So the question is that can you find an explicit function such that its quantum complexity is only logarithmic, but classically it has to be a power of n. And just to summarize what we have done, and what I like to hope I have done is to show you that the considerations from communication have a huge impact on computational complexity development in the last 30 years. And secondly, that there are really huge problems, open problems in computational complexity that can be phrased as communication problems that I think that all of you can understand, and I believe that and I hope that you will find it interesting and choose to come to solve some of these problems. And thank you very much.
Okay, since we have to keep up with the schedule, I would suggest that if there's any question from the audience, we'll leave it offline. Professor Yao